Given question, a solid shaft AB is rigidly connected at its ends to two hollow shafts AC and BD as shown in diagram. At C and D, two rotors having mass 135 kg and 350 kg with radius of gyration of 0.4 meter and 0.6 meter respectively are attached to the free end of the hollow shaft. Determine the natural frequency of torsional vibration and the position of the node. Assume G is equal to 83 into 10 raised to 9 Newton per meter square.
Let us understand given question. At the two ends of the hollow shaft at A and B, solid shaft is connected rigidly. Now the diagram is given, and for the solid shaft, outer diameter 0.16 meter and inner diameter is 0.1 meter. For the hollow shaft, diameter is given 0.08 meter. Now at the end A, the length of the solid shaft is given 0.6 meter, and at the end B, the length of the solid shaft is given 0.4 meter, and the whole length of this shaft, that is the hollow shaft, is given 1.6 meter. Now if we observe this diagram, at the end C and D, that is at the inside of this solid shaft, the rotors are connected, whose mass as well as radius of gyration is mentioned in the question. Now we will rearrange this diagram. So we will rearrange because we have to place these rotors, that is this point C and D, at the ends of the hollow shaft. So how to rearrange this diagram? So we will now consider only first section, whose length is 0.6 meters. So I will mention here the first section whose length is 0.6 meter, and this is known as L1 because this is the first section. Now we will replace this point C at the end here, that is we will just place this point C at the first end. So I will write here, this is the point C where the rotor is placed, and the end A to the inside. So I will write here, this is the end A. Now what about this outer diameter? So this is the section 1. So outer diameter is known as DO1 and it is 0.16. So we have to write here DO1 is equal to 0.16. Now in the same way, inner diameter for the solid shaft is 0.1 meter. So we will write here DI1 because inside diameter. So DI1 is equal to 0.1 meter. Now we will move to the next section. So next section, that is in between, in the first diagram, in between the C and D. But we have rearranged this diagram. So here in the same way we have to also rearrange this solid shaft, and here will be end B. So now in between these points A and B, remaining length. So if we observe this 0.6 plus 0.4, that is 1. So remaining middle length, that is equal to 0.6 meter. So again we will mention here 0.6, and this is the second section, that is length L2. Now for this length L2, diameter for the hollow shaft is given, that is D2 is equal to 0.08. So we will write here D2 is equal to 0.08. So I will write here D2 0.08. So this is the diameter of the hollow shaft. Now we will move to the third section. So for third section, length L3 is given 0.4. So 0.4 meter, and this is the length L3. Now here we have to place point D at the end point. So here for the rotor, this is the point D, and this outer point we have to place to the inside. Now what is the outer diameter? So same outer diameter, that is 0.16. So for this outer diameter, this is the section 3. So we will say DO3. So we will say here DO3, and that is equal to 0.16. And in the same way, inner diameter is 0.1. So inner diameter for the section 3, that is DI3. So we will write here DI3 is equal to 0.1. Now we will take the reference for this rearrangement of the diagram and we will solve the question. Two rotors are placed at points C and D. So we will calculate the mass moment of inertia of these two rotors. So mass moment of inertia I is equal to mass into radius of gyration square. So the mass and radius of gyration for each rotor is mentioned in the question. IC is equal to mckc square, which is equal to 21.6 kilogram meter square. ID, that is mass moment of inertia of the rotor placed at D, is equal to mdkd square, which is equal to 126 kilogram meter square. Now if we observe the given question, this system is having different diameters with different length. So in this actual system we will replace with equivalent system with uniform diameter and equivalent length. So we have to assume that uniform diameter. So if I replace this uneven shaft, that is with diameter and length, with uniform diameter, then D equivalent. So we will assume any particular value. So I will consider here D equivalent is equal to 0.5 meter. Then for this diameter, that is equivalent diameter, we have to calculate the equivalent length. So how to calculate this equivalent length? So we have to take the reference for this actual system and we will write here the formula. So L equivalent is equal to, now if we observe the first section, it is having outer diameter and inner diameter. So we have to refer this, and also we have to refer the equivalent diameter and with length L1. So here L equivalent is equal to L1 into D equivalent raised to 4 divided by, now we have to take the difference, that is DO1 raised to 4 minus DI1 raised to 4, because we have to consider only the solid part. So solid part is having outer diameter 0.16 and inner diameter 0.1. Plus, now we will move to the second section. So for second section, L2 multiplied by D equivalent raised to 4 divided by D2 raised to 4. So here only single diameter, that is for the hollow shaft. So we have to refer here the D equivalent by D2 raised to 4. Plus, now we will move to the third section, that is L3. So L3 multiplied by D equivalent raised to 4 divided by DO3 raised to 4 minus DI3 raised to 4, because we have to consider only the solid part of the shaft, which is having outer diameter as well as inside diameter. So when we put the values, because all the values are known, then we have to calculate this. So here DO1 is equal to 0.16 raised to 4 and DI1, that is 0.1 raised to 4. So in the same way here DO3, that is 0.16 raised to 4 and DI3, that is 0.1 raised to 4. So we will put the values and we will calculate this, and final we will get the answer. Equivalent length is equal to 1028.06 meter. Its unit is meter. Now for this equivalent system, we will find the position of node. We know that the rotors placed at C and D rotate in opposite direction and that cause the torsional vibration. So I will show here the rotation, that is if this rotor at C rotate in clockwise direction, then the rotor at D will rotate in anti-clockwise direction and it will cause the torsional vibration. So the amplitude developed at the end C and at the end D are in opposite direction. So we will show here. If we draw here the horizontal line, then the amplitude A1 at point C is in the upward direction, then the amplitude at point D should be in opposite direction, that is in the downward direction. So this A1 and A2 are in opposite direction. So if we join these two ends of the amplitude, then we get here one point of intersection with this horizontal line, and this is known as the node point, that is N. And at this point N, the amplitude of vibration is 0. Now if we measure the distance from this point C up to point N, then it is known as LC. and if we measure the distance of this point N from point D, then it is known as LD. Now we will find out this value of LC as well as LD. So how to find out this? So we have one condition, that is ICLC is equal to ICIDLD. So here D is there. Now what is this IC? That is the mass moment of inertia at point C multiplied by LC is equal to mass moment of inertia at point D multiplied by LD. Now we will put the value. So we know IC and ID that we have calculated. So when we put, we will get the relation in between LC and LD. So this is the equation number 1. Now this is the node point for the equivalent system. Now from the diagram we can say that L equivalent is equal to LC plus LD. So this is the equation number 2. So we will put the L equivalent, that is 1028.06. Now from this equation number 1, if we put LC is equal to 5.833 LD, then we can take LD as a common term, and inside the bracket 1 plus 5.833 is equal to 1028.06. So LD is equal to 150.44. And now if we put the value of LD in equation number 1, then we will get LC is equal to 877.55. Now we get the two values LC as well as LD, that is the distance of node point from the end C and D. Now next question is to calculate natural frequency, and this natural frequency is applicable for this equivalent system. So what is the formula? So we have formula Fn is equal to, now this natural frequency is same for both the ends, that is at point C as well as at point D. So we will write the formula 1 by 2 pi under root of J equivalent ICLC is equal to 1 by 2 pi under root of J equivalent IDLT. Now what is this G? Modulus of rigidity, and its value is 83 into 10 raised to 9 Newton per meter square, and it is applicable for this shaft material, and it is mentioned in the question. So for this end C as well as end D, shaft material is same, so this value is also same. Now what is J equivalent? So this J equivalent is the polar moment of inertia for this equivalent system. So this node point is applicable, that is this node point is for this equivalent system. So we have to calculate here J equivalent. So this polar moment of inertia, why it is developed? Because it is resistance to the torsional vibration that occurs at this because of the ends of the rotor. So when the rotors rotate in opposite direction, then the vibration occurs, and these rotors are connected to the shaft, and that's why there is the resistance that is getting acted in this shaft. And this formula J equivalent is equal to pi by 32 into D equivalent raised to 4. So by using this formula we can calculate J equivalent. Now next is ICLC. So IC we have calculated, LC that is here. That is, this is the value 877.55. In the same way IDLD is also known. Now we can take any one formula to calculate natural frequency. So when we put the value, we will get the answer 26.08 Hz.